It is good to be here. Just by way of introduction, my name is Danny Call. I'm currently a graduate student at Colorado State University in their Systems Engineering PhD program. In my day job, I'm a civilian engineer for the Air Force. So maybe, and we know Mark noticed the reference in my title to the movie, The Field of Dreams. In that movie, Kevin Costner hears a mysterious voice telling him, if you build it, he will come, meaning plow out down his cornfield, put a baseball diamond in so he can play catch with his dead dad. This is misquoted often, though, to if you build it, they will come. And it's been used as a motivational quip to get across the meaning that you just need to be bold, put yourself out there. If you develop and you provide the right product or service, the demand and market will materialize and adoption will occur. So what does this mean for us systems engineers? Well, we recognize this image on the left as a document-based approach to systems engineering, right? As modern systems get more and more complex, this hasn't been adequate to keep up with things. So we have been bold, we have built it, and we have come up with a model-based paradigm, model-based systems engineering. Now, in this group, I'm not going to belabor the point of the benefits of model-based systems engineering. I'll just say that they're out there. However, on the left, we call that systems engineering, and on the right, we call it model-based systems engineering, implying that this isn't our standard way of doing things. And as Mark pointed out really well, this isn't a technical problem anymore. This is a people problem. So where do we go from here? Michael Griffin, a former NASA administrator and Undersecretary of Defense, had this to say: until and unless we begin to delve into the social and cognitive aspects of how engineers work together and how systems engineering is performed, possible contributions from fields far apart from engineering will continue to go unrecognized. The study of human interactions, cognitive psychology, social choice theory, and other disciplines must be included in the development of effective theories of systems engineering. So one of those fields far apart from engineering that I'd like to discuss with you today is the study of how innovations are diffused throughout a society. And this is captured very well by Everett Rogers in his book, Diffusion of Innovations. The first edition of this book was published way back in 1962, and this fifth edition was published in 2003. Rogers was a rural sociologist studying how hybrid corn and different chemicals and other agricultural innovations were adopted, and why some with similar benefits were adopted slower than others or not at all. So he observed that every innovation, no matter how popular it is not adopted instantaneously. It follows this adoption S-curve. You start out with the innovators and early adopters starting to figure it out. Then as the early majority adopts it, it really takes off. And then the late majority starts to adopt, and that curve starts to flatten out as the laggards, the last that will eventually adopt, finally do adopt. Now, this is a generalized S-curve because some innovations are adopted in a matter of weeks, like a stupid viral video on YouTube. Others, especially in the defense industry, may take years or decades, but they all follow this curve. Additionally, the percentage of adopters varies from innovation to innovation. Some specialized innovations may only be adopted by a small percentage, while that viral YouTube video is a much higher percentage. So to understand why there's variation, well, he identified 5 variables that help us understand that variation. The perceived attributes of the innovation itself, the type of decision that goes into deciding if they're going to adopt, the communication channels that are used to spread word about that innovation, the nature of the social system that's considering adoption, and finally, the extent of the change agent's promotion efforts. Now, all these are important, but Rogers found that 49 to 87% of the variance in adoption rate can be described by the perceived attributes of innovation. So that's where I'm going to focus today. So relative advantage is very straightforward. The degree to which an innovation is perceived as being better than the idea that it supersedes. This can be measured in economic terms, in prestige or performance, or any number of value measures that you have. It also explains why preventative innovations like seat belts are slower to be adopted, because the advantage is a non-event, and thus it's harder for people to perceive that advantage. Second is compatibility, the degree to which an innovation is perceived as consistent with the existing values, past experiences, and needs of the potential adopters. This is because people aren't going out and doing a trade study every time they make a decision. They will make decisions based on their own mental models, what they understand and what they're familiar with. They will also evaluate it based on the need, a relevant need that they have. So next is complexity. And this is the only one that's negatively correlated with adoption rate. And it's the degree to which an innovation is perceived as relatively difficult to understand and use. If it looks hard, it's going to be adopted more slowly. Trialability is a degree to which an innovation may be experimented with on a limited basis. So people need to reduce the uncertainty of adoption by trying it out. So innovations with a high cost of entry are slower to be adopted, but if you can get in and try it out easier, it increases the adoption rate. And finally, observability, the degree to which the results of the innovation are visible to others. So if it's a lawnmower that can have a wider cutting swath than a narrower one, that's directly observable, and that can be adopted faster than an innovation that requires a high degree of domain knowledge to understand. Now, really quick in 60 seconds here, I just want to have an example of how this applies to a technological innovation. So some of you may have heard of a Dvorak keyboard. The standard QWERTY keyboard that we're all familiar with was developed in the late 1800s as keyboards were coming online, as typewriters were coming online. And it wasn't designed to be inefficient, but it wasn't optimized for efficiency because those early keyboards would jam if you hit two keys next to each other too quickly. By the early 1900s, typewriter technology had improved enough that this was no longer a concern. So Dvorak studied for 10 years all the things that slowed people down typing and came up with an optimized keyboard layout. However, we still use the QWERTY keyboard layout, even though it's not the best layout by objective and quantifiable means. The diffusion of innovation theory can explain why the Dvorak keyboard was not adopted. First of all, relative advantage. We all know people that can type just fine on a QWERTY keyboard. We don't see a huge advantage in changing layouts. The compatibility, once you learn how to do it, it's not compatible with our standard keyboards, and it's not compatible with the need because we don't see a need. Complexity. The QWERTY keyboard is what we're used to seeing when we talk about keyboards. A Dvorak keyboard is not familiar to us and appears very complex. Trialability is low because you have to have specific training to use a Dvorak keyboard and realize any kind of benefit. And finally, observability. If you saw someone effectively using a Dvorak keyboard and someone using a QWERTY keyboard, you would not be able to directly observe any difference unless you were trained in typing physiology. So through the lens of diffusion of innovation theory, it'd be more surprising if the Dvorak keyboard layout had taken off as opposed to the fact that it really hasn't. So now I want to look at model-based systems engineering through the lens of the diffusion of innovation theory. Look at how we might perceive model-based systems engineering according to each of these attributes. So first of all, relative advantage. So the relative advantage of model-based systems engineering may be lower due to the early upfront costs that's required for the culture change, for the investment in tools, these different things. Many of you may have seen a graph like this in the past of the early upfront costs required for a model-based systems engineering approach that are recouped later on in savings, but that upfront cost is real. Also, model-based systems engineering is a preventative innovation. So you're preventing bad things from happening. You're preventing integration challenges from happening later, and that's hard to directly observe. So what opportunities do we have to maybe change the perception of relative advantage for MBSE? Well, we can be really upfront in recognizing the upfront cost and help stakeholders who are making a decision understand the lifecycle cost and what they're gaining from transitioning to model-based systems engineering in the long run. Maybe there's room for more development of open source solutions to lower that initial spike so that we can see that advantage sooner. And finally, improving our design quality metrics so that, again, we can clearly show the problems that we avoided, those in the seatbelt example, those injuries and deaths that were prevented from using model-based systems engineering later. So compatibility, the current perception is that model-based systems engineering is something new and different. This is a buzzword, right? And also, sometimes it's hard to see exactly what the need model-based systems engineering meets. So the opportunity to improve that perception is highlighted. Okay, model-based systems engineering is not a new thing. The SE in model-based systems engineering is systems engineering. And we need to take an organization's existing systems engineering processes and tailor our MBSE methodology to take advantage of that so that we're using our stakeholders' existing mental models of how they do systems engineering as they do model-based systems engineering. And we need to focus on the needs that MBSE meets, highlight the ability to enforce consistency in our system specifications, the ability to reduce errors, and the fact that our system model in the MBSE approach can serve as an authoritative source of truth for our systems engineering information. So complexity. The current perception is that it's high. It's very complex. So as systems engineers, we're used to dealing with complex systems, but as an engineer, we're doing most of our work in productivity tools like Word, PowerPoint, Excel, Visio. Maybe we'll deal with a requirements database, but these are all things that we can pick up and learn. When we talk about model-based systems engineering, we're talking about a new language, new tools, and new processes. So the perception is that it's very complex, and to a degree, it may be. So what are our opportunities to improve the perceived complexity? Well, first, and I like the previous presentation's highlight of this, is have a clear modeling purpose, because that provides context. When we have context for why we're doing MBSE, stakeholders who may not know the ins and outs of MBSE, if they know why we're doing it, they can look and see, okay, I see what you're doing here. We don't do MBSE just to do MBSE. And we need to make sure that those people who are asking us to help them start with MBSE, that they have a clear purpose in mind, and that will reduce that complexity. Secondly is having established roles, recognizing that not everyone on a team needs to know how to use a modeling tool inside and out. That if we tailor our training and tasking to specific roles, we can reduce the complexity. If someone only needs to be able to look at a SysML diagram, let's make sure that we only train them on SysML and don't get them lost in how to use a new modeling tool. And actually, I will throw out one last one. I appreciate the presentation from the University of Michigan, because that's another great opportunity here for reducing complexity, is to increase exposure to these things in undergraduate engineering programs. Trialability. The current perception is MBSE is all or nothing. You're doing it or you're not. And that there is a high cost of entry. So as we talked about earlier with this spike. So the opportunity is, as we introduce MBSE to organizations, focus on the fact that a model is complete when it answers the question that you set out to answer. So you don't need to model your entire system to get value from an MBSE approach. Choose a single mission thread. Single capability, create a system model that answers the questions you need about that, so that you can show your stakeholder value early on and limit that modeling scope. Again, if we can increase our open source opportunities for tools and things, that can reduce the upfront cost, but also as organizations looking to adopt MBSE, these tool vendors are fantastic. They produce wonderful tools, and they have a vested interest in helping us get started. So utilize trial licenses, utilize training from vendors so that we can try it out and show value for our stakeholders and get started with it. And finally, observability. The current perception is it's hard to see problems that are prevented. So again, one way that we can increase the observability of the benefits of model-based systems engineering is conduct design reviews and working groups directly from the modeling tool. Let all of your stakeholders see the times that consistency is enforced because of your model. Let your stakeholders see when ambiguity was reduced through using your system model. Let them see the benefits of the object-oriented principles like modularity, encapsulation, reuse, inheritance as you're working in your system model. So those stakeholders can see the benefits of model-based systems engineering. Again, improve design quality metrics so that as we're comparing side by side with a document-based approach, that we can see that we actually are removing defects from our systems and improving the systems engineering quality. So future work, and this is for me. I mentioned I'm a graduate student. I've just talked today about what diffusion of innovation theory maybe can explain about model-based systems engineering. These have just been some ideas. So some future work would be to do an actual structured study to determine how exactly the diffusion of innovation theory applies to model-based systems engineering, and how organizations that are considering adopting model-based systems engineering, those who have tried and failed, and those who have successfully adopted systems engineering, how they would rate or evaluate model-based systems engineering based on these attributes. So we can see if there is a correlation between the diffusion of innovation theory and model-based systems engineering. And then I would like to take the results of that study to inform a better way forward to how we can better present model-based systems engineering to potential adopters. The ideas that I gave today, those are some thoughts, but I would like to have some good data to substantiate some of those opportunities and suggestions going forward. And then also investigate those other variables that the diffusion of innovation theory offers. So again, Rogers found that between 49 to 87% of the variance is due to the perceived attributes of innovations. But for model-based systems engineering, we don't know which end of the spectrum it lies on. So I would like to investigate further how the type of innovation decision affects it. You know, communication channels, the nature of the social system, if having a system or a change agent promoting it, having that champion for model-based systems engineering within an organization really helps out. So just in conclusion, I'd like to say model-based systems engineering has come a long way, and in no small part to efforts of many in this room. We have built it, we have been bold, and now we need to maybe look to some other areas, some social science areas, to see how we can help the people come so that we can take advantage of the opportunities that model-based systems engineering offers for our systems engineering community. So thank you.